This is the second part of our two-part series on expected value and variance. Recall that in studying a random variable x, it's important to ask not only what's the typical value of x, but how much variability is there in x from observation to observation. In visualizing and measuring variability, what we're precisely interested in is how far individual outcomes of x tend to be from the typical value of x. For example, consider the PDFs here of x and z, the commute times for two different routes that your friend takes to school. Notice that the typical time to school is roughly 20 minutes for both routes. Yet, on average, the commute times for the second route, represented by variable z, tend to fall further from this average. That is, there's more variability in the commute times for the second route. In this video, we'll explore how to measure this variability. This will come down to examining distances, or how far we expect an individual outcome of x to fall from the typical value of x. First, let's consider how we calculate variability in a sample of data points. The plot at left displays a histogram of 1,000 observed commute times x. Notice that the typical commute time is around 20. More precisely, the average commute time is 20.07 minutes, which we calculated by adding up all 1,000 commute times and dividing by the sample size, 1,000. If you've taken an introductory statistics course, you also learned, but don't necessarily remember, that the variance in commute times measures the typical squared distance of an observed commute time from the average commute time. That is, the variance in the commute times measures the typical squared distance of an observed commute time from the average commute time. Mathematically, the variance is essentially calculated by averaging up the squared difference between each observation xi and the sample mean x bar. I say essentially average up here, since we sum up the squared differences in the numerator and divide them not by the sample size 1,000, but by the sample size minus 1, a minor distinction when the sample size is this large. In our example, the commute times have a variance of 3.82 minutes squared. That is, on the typical day, the squared distance between your friend's commute time and the 20.07 minute average will be 3.82 minutes squared. It's important to note here that since we're measuring squared distances, the variance has squared units. But this makes the variance a little awkward to interpret. Hence, we typically measure the variability of a sample by the standard deviation, or the square root of the variance. This measures the typical distance, not squared distance, of an observed commute time from the average. To make it easier to remember this measurement, note that another way to refer to a typical distance is standard deviation, hence the name. In our example, the commute times have a standard deviation of 1.595 minutes. Thus, on any given day, we expect your friend's commute time to deviate by 1.95 minutes from the 20.07 minute average. Stepping back, our sample has an average commute time of 20.07 minutes. And on a typical day, we expect that your friend's commute time will fall 1.95 minutes above or below this average. Again, this is just the expected or typical deviation from the average. It's possible that your friend's commute time is closer to or falls even further from the average. All right, let's connect the concept of measuring the variability of sample data with measuring the variability of the underlying probability model. Just as with sample data, the variance of a random variable x measures the expected or typical squared distance of an observed value x from the mean e of x. The formula for the variance follows from this definition. It's the expected squared distance of an observed x value from its mean e of x. We will also prove in class that we can rewrite the variance of x as the expected value of x squared minus the expected value of x quantity squared. Personally speaking, I find this statement of the variance to lose the meaning of the measurement, mainly the meaning of the variance as expected squared distances. But in most cases, this formula is easier to calculate. Finally, as was true for measuring the variability in data, we'll often report the standard deviation of a random variable. This puts the measurement on the original units of our variable, measuring the expected distance, not square distance, between the observed outcome and the mean. Finally, let's apply this result to our example of the soda machine. Recall that x measures the error in the amount of soda poured into a can in ounces. In the previous video, we showed that the expected error is negative 0.2 ounces, and the expected squared error is 1 ounce squared. Thus, all we need to do to calculate the variance in errors from can to can is to plug these numbers into our second formula for variance. Specifically, the variance in x is 1 minus negative 0.2 quantity squared, or 0.96 squared ounces. Taking the square root, the standard deviation in x is 0.98 ounces. That is, when the machine fills a can of soda, we can expect its error to be 0.98 ounces from the mean of negative 0.2 ounces. For completion's sake, we can also take the more tedious route of calculating the variance by plugging through our first formula. Notice here that the variance is the expected value of a function of x. Thus, we can evaluate this function at each possible outcome of x and weight the results by the corresponding probabilities of those outcomes. For example, notice that x equals negative 1 with probability 0.5. Correspondingly, we observed a squared difference between x equals negative 1 and the mean, negative 0.2, with probability 0.5. Similarly, x equals 0 with probability 0.3. Thus, we observed a squared difference between x equals 0 and its mean, negative 0.2, with probability 0.3. The result is the same as before. X has a variance of 0.96 squared ounces.